Okay, so we're going to be talking about alternating series in section 9.5. Up to this point, all the series that we've encountered, the terms have only been positive to keep things simple. Today we're going to be talking about alternating series since these series will come up in the work that we're going to do. So an alternating series is a series whose terms alternate in sign. And so when we were talking about sequences, we said that this factor of -1 to the k plus 1 will make your terms alternate positive, negative, positive, negative. So here we're assuming that a sub k is a positive sequence where all the terms are positive, and what this -1 to the k plus 1 is going to do is make it alternate. Also, we could have had a -1 to the k. That will also make it alternate. And so if we see either of these two factors in our terms and the a sub k's are positive, then we're looking at an alternating series. Okay. And so in the case of an alternating series, it turns out that we have this theorem that tells us that an alternating series of either form 1, where you start with a positive and then a negative and then a positive and then a negative, or a form 2, where you start with a negative and then a positive and then a negative and then a positive. Either one of those are going to converge as long as the following two conditions are satisfied. First condition is A1 is bigger than A2, and A2 is bigger than or equal to A3, and A3 is bigger than or equal to A4, and so on. And all that's saying is that the, the terms of the sequence are decreasing of the positive sequence of the absolute values, right? Because we're not looking at that factor of -1 in this inequality. Also, the terms have to be going to 0. So we've already gone over that if your terms don't go to 0, your series cannot converge. And so here, as long as these two things happen, your series is going to converge. So we're not going to go through a formal proof of this, but it's kind of neat to see what's going on here. This picture that you see here at the bottom illustrates why this is true, right? So if you look at the sequence of partial sums, S1 is just A1. And so they put S1 right here. And so S1 is on the real number line. It's a real number. It's just the sum of the first term, and it's just the same as S1. Now, S2 is just to take S1 and add the next term, A2. And so you see that here that you're starting here at A1 and you're moving to the left now because A2 was negative, because it was a negative number, right? We're using the positive, negative type, but a similar argument could be made for the other one. Okay, now S3 is just S2, and you're adding the next term, A3. But again, when you went back A2, since A2 was smaller, that's why it's important to have a decreasing sequence, because A2 was smaller. You didn't go far as back as A1 had brought you to the right. You didn't go as far back to the left as A1 had brought you to the right. And so now with A3, now you're going to go to the right, but not as far as you had come back to the left. And so then S4, you're going to take S3 and you're going to add the next term, A4. And so then now you're over here at S3, and now you're moving to the right. That's why it's important that these be alternating in sign. You just keep bouncing back and forth and back and forth. And then we'll do one more. S5 will just be S4 plus A5. And again, as you bounce now back to the right, you don't go back as far as you came to the left, and you're just going to keep bouncing back and forth and bouncing back and forth. You can see geometrically that you're going to be getting closer and closer to one specific number, and so then your limit of the sequence of partial sums, the limit as n goes off to infinity of the S sub n's will exist. That's not a formal proof, that's relying on this picture, but that builds some intuition, and that's good enough. So again, we're going to apply this theorem. When I reference this theorem, I'm going to say by AST, alternating series test, right? To apply this theorem, we're going to need our series to be, the terms of the positive sequence to be decreasing, right? And we're going to need the terms to go to 0. So up first is this problem. Now you see here your factor. That is going to make it alternate because everything else is positive, n, and the 3n plus 2 is positive. So this is going to alternate, right? But when the a sub n in this problem would just be given to us by the formula n over 3n plus 2. And just by looking at that, you should know that the limit as n goes off to infinity of the terms is going to be 1/3 because it's a rational expression where the degree of the numerator is the same as the degree of the denominator. You're just going to get the leading coefficient of the numerator over the leading coefficient of the denominator. If you want to go through the work, you can remember that how we did this is by multiplying the numerator and denominator by 1 over the largest power in the denominator. But when the degrees were the same, all the terms except the ones in front were going to go to 0. And the ones in front were just going to be the coefficient of the first term over the coefficient of the last term. So let's move on. So determined the convergence or divergence of this expression, right? Now this one you don't see the factor of -1 as we did in the last one, but it really is there. You can rearrange this series. This is the summation, and I'm not going to write the limits of integration just so that I don't have to write so much. But this is just the summation. I'm sorry, the limits of summation. But this is just the summation of n over -1 to the n minus 1 times 2 to the n minus 1. And there you have your factor of n minus 1. So you can see that you have your factor there. And so in this problem, the a sub n is n over 2 to the n minus 1. And we have to show two things in order to apply the alternating series test. We have to show that the terms go to 0. And so then that means that we want to show that the limit as n goes off to infinity of the a sub n is 0. But what you should recognize is that as n gets bigger and bigger, both the numerator and the denominator get bigger and bigger. And so then you should recognize that this is a place for L'Hopital. And again, when you're using L'Hopital, what you should do is change this to the limit as x goes off to infinity of x over 2 to the x minus 1. Okay, now again, we can exchange this by L'Hopital. For the limit as x goes off to infinity of the derivative of the numerator, 1, over the derivative of the denominator. And so that will be, since it's 2 to the x minus 1, that's an exponential function, but it's to the x minus 1, not to the x, so we have a composition there. So if you remember the derivative of exponential function whose base is not e, you get this extra factor of the natural log of 2 times 2, same inside, x minus 1, times the derivative of the inside, but that's just 1. And now the numerator is fixed at 1. The denominator is got this 2 to the x minus 1, which keeps growing and growing without bound. So this limit is 0. And so we've got that part. But next we want to show that the series or sorry, the absolute values, the a sub n is decreasing, right? And so again, let me go through this one in detail. Um, um, so to do that, what we'll show is that a sub n plus 1 over a sub n is less than 1, less than or equal to. Because if we can show that, then if we multiply both sides of this inequality by a sub n, we have that a sub n plus 1 will be less than or equal to a sub n. So that means any term is less than or equal to the term before it, and that means that it's decreasing, right? So that's what we get to. So one way of showing that it's decreasing is to show that the ratio of a sub n plus 1 over a sub n is less than 1. So again, a sub n plus 1 is just the term that you get when you put in n plus 1 in for n. So you will get an n plus 1 in the numerator and a 2 to the n plus 1 minus 1 in the denominator. But when this cleans up to n plus 1 over 2 to the n. Okay, and so then when we go and we divide a sub n plus 1 by a sub n, since we're dealing with fractions rather than dividing, we're going to multiply by the reciprocal. So we're going to take the 2 to the n plus 1 over 2 to the n, and we're going to multiply it by the reciprocal of a sub n, and the reciprocal of a sub n is 2 to the n minus 1 over n. And so then what we get here, let me rearrange things. So what we get here is the n plus 1, we multiply fractions by multiplying straight across, so we get n plus 1 over n. And then here, notice that these have the same base. And so then when we have the same base, we subtract, and we're dividing, we can subtract the exponents. The exponent here is n, the exponent here is, I'm sorry, n minus 1, the exponent here is n. So n minus 1 minus n is just minus 1. So we end up with a 2 to the minus 1. And then we can rewrite that as n plus 1 over 2n. Now, you should recognize that except for n being 1, if you add 1 to a number, to an integer, to a natural number, whole number, you're going to be less than if you multiply that number by 2. So adding 1 is less than multiplying by 2 as long as n is bigger than 1. And here's another thing. It doesn't matter if it's always decreasing as long as it's eventually decreasing. What happens in the first couple terms doesn't matter, right? So maybe it'll be decreasing after the first 100 terms, and that's okay, because we could add those first 100 terms up beforehand. That will be finite. We add it with the rest of it, and so the whole thing will be finite. But here, n plus 1 is, after 1 is going to be less than 1, therefore decreasing. Therefore, your series converges by alternating series test. Now, this ratio of a sub n plus 1 divided by a sub n, we're going to do in other problems. And so you need to get comfortable with doing that, right? So I've tried to do that here for you slowly. You find your a sub n plus 1 by substituting in n plus 1 everywhere you see an n, clean it up. And then to form your ratio, you just take your a sub n plus 1 if you have fractions and multiply it by the reciprocal of a sub n. Okay, so let's move on. Okay, so here we do have our nice little factor of -1 to the n plus 1. So clearly this thing is alternating, right? Um, Next, we need to show that the terms go to 0. And so then that's pretty clear that the limit as n goes off to infinity of n over n squared plus 5 is 0. Again, I forgot to mention, right, that a sub n in this case would be the sequence n over n squared plus 5. We're adding up the alternating terms of this sequence, right? And so then the limit of the terms, the limit as n goes off to infinity, is 0. Okay, and because it's alternating, next we just have to show that it's decreasing. Remember, decreasing is the whole reason we were able to make that argument that once you go in the other direction, you don't go back as far, and so you keep bouncing between the two, getting closer and closer to 0. So we have to show that it's decreasing. So again, getting comfortable with this a sub n plus 1 is just going and substituting in n plus 1 in for n. So there's an n right there. We replace it with n plus 1. There's an n right there. And so we get n plus 1 squared plus 5. Okay. And so then this becomes n plus 1 over 2n squared. Sorry, not 2n squared. Over n squared plus 2n plus 1. And then plus this 5 will give us a plus 6. Okay. And so then we to our a sub n plus 1 divided by our a sub n is going to be our n plus 1 divided by n squared plus 2n plus 6 times the reciprocal of a sub n. And the reciprocal of a sub n is going to be n squared plus 5 over n. And so then this ratio will be, let's multiply this out. So when we distribute in the denominator, we get n cubed plus 2n squared plus 6n. And when we distribute in the numerator all the terms of one times all the terms of the other one, so the n times the n squared will give us n cubed. The 1 times the n squared will give us n squared. The n times the 5 will give us 5n. And last, the 1 times the 5 will give us 5. Right? No like terms, and there we go. Now here, again, notice that when n is 1, 1 plus 1 is 2, plus 5 is 7, and 5 is 12. But in the denominator, we get 1 plus 2 is 3, plus 6 is 9. And so here, our fraction when n is 1 is bigger than 1. But if you compare, you have the n cubes. Here you have n squared, and here you have 2n squared. We have more of the n squared. Everything is positive. Here you have 5n, and here you have 6n, and here you have this extra term of 5, right? So you have more of the n squareds and more of the n's in the denominator. And so even though for 1 you get something that is bigger than 1, once you get past, I think maybe even 2, let's see for 2 you get 8 plus 4 plus 20 plus 5, and then you get 8 plus 8 plus 12. So here you will get 28. Here you will get 32. Actually, even for 2, the numerator is still bigger. But eventually, adding the n squared and the extra n, you will get more than adding the 5, right? That's the difference between the two, right? And so eventually, the n squared, the extra n squared and the extra n will give you more than 5. So eventually, a sub n plus 1 divided by a sub n will be less than 1. which implies therefore decreasing. Okay? And since it's decreasing, therefore converges by the alternating series test. Okay, so that's what we had to do. Determine whether the alternating series converges. Justify your answer. Okay, so again, we have an alternating series. There's our term right there. We have the a sub n is equal to the natural log of k divided by k. Okay, and again, notice that your series here starts at 3. It doesn't start at 1. And the reason why we're not starting at 1 is so that uh, you only have positive terms, right? So natural log of 1 is 0. And then again, you also want it to be decreasing. And if we go from 3 on, then it will always be decreasing, as we're going to show in just a little bit. But that's really not important. It could have started at 1, because the first finite terms, as long as they're defined, the first finite number of terms don't matter. Okay, so here, looking at the ratio, a sub k plus 1 divided by a sub k is not going to be very useful. Not going to be obvious to show that that is decreasing. So what we can do, we could always use the calculus. We can look at f of x equals the natural log of k. I'm sorry, the natural log of x and divided by x. We could find f prime of x. This is a quotient, so we'll use the quotient rule. The derivative of the numerator is 1 over x times the bottom left alone, 1, minus, take the derivative of the denominator, 1 times the natural log of x. And in the denominator, we get the natural log of x. We get x squared, right? And so notice that the denominator is always positive, and so for this function, the x has to be bigger than 0, right? So then when we look at the sign chart for this, we need the critical numbers, the numbers that make the derivative 0 or undefined. This starts at 0, and it is a point where my derivative is undefined. My function is also undefined, but we also need the critical numbers, and the only critical number is the number that makes the numerator 0, because the only number that makes the denominator 0 is 0. So if you figure out what makes the natural log 1, then that's your critical number. And again, you could do that. Let's go ahead and do that up here. The natural log of x minus 1 needs to, I'm sorry, went backwards. 1 minus the natural log of x needs to equal 0. So 1 needs to equal the natural log of x. You can exponentiate, and then you will get that x needs to equal e. Okay, so the only critical number is at e. If you, e is 2.7, so if you plug in 1, and the natural log of 1 is 0, 1 minus 0 is 1, over 1 squared is 1. And so then over here, you're going to get a positive value. Once you get past e, you can see that since the natural log gets bigger and bigger without bound, once you pick in a really big number, this will be bigger than 1. 1 minus a number bigger than 1 will be negative. So you can put in 4 or 5 if you want into your calculator, but you should know from what the natural log does that this just increases without bound. So eventually it's going to be bigger than 1. So eventually this will be negative, and that eventually is as soon as you get past e. So over here it's either always positive or always negative. So we don't really need a calculator for that. So we've just shown that it's decreasing because again we started at a k value of 3, but it really wasn't necessary to start at 3. We could have started at 1 or 2. and we would still just say eventually it's decreasing, so we're good. Okay, so it's alternating. The terms are going to zero, but we also, we need to look at, make sure the terms are going to zero. I'm sorry. We haven't shown that. So again, to show that the terms are going to zero, we can use L'Hopital. So take the limit as x goes off to infinity of the natural log of x over x. Both the numerator and denominator increase without bound. So we can exchange this for the limit as x goes off to infinity of 1 over x. Because the derivative of x is 1, we're left with is just the natural log of x, and no need to write it over 1. And this is by L'Hopital. Okay, but the limit as x goes off to infinity of 1 over x is 0. So we've shown both things. We've shown that the the sequence of the absolute values is negative, is decreasing, and that the terms are going to 0. And so then therefore converges by alternating series test. So let's move on. And so again, what we have here is it's alternating. So we're good there. But again, we look at our a sub n, and we see n squared over n squared plus 4. I know it's got to be difficult for you guys to just watch these videos. These aren't the most exciting videos in the world. So what I suggest is that you pause, try the problem on your own, and then hit play and see if you got it right. When you see this, you should automatically recognize that the degree of the numerator and the denominator are the same. These are just a rational function. And so then the limit as n goes off to infinity of a sub n is just going to be 1. The leading coefficient in the numerator divided by the leading coefficient of the denominator. But they need to go to 0. Therefore, diverges. Doesn't matter that it's alternating or not. Your terms have to go to 0, and these go to 1. So this series diverges. Okay, so again, the best thing is to try this yourself. But here we have the a sub n. You have your factor of -1 to the n plus 1. Your a sub n is going to equal the natural log of n plus 1 divided by n plus 1. If we take the limit as n goes off to infinity of the a sub n, we can do that by taking the limit as x goes off to infinity of the natural log of x plus 1 divided by the natural log of x. I'm sorry, no natural log, just x plus 1 on the bottom. And this is infinity over infinity, so we can L'Hopital it. The derivative of the denominator is 1, so by L'Hopital. We can replace this limit with the limit as x goes off to infinity of the derivative of the numerator. That's a composition, so it's 1 over the inside times the derivative of the inside, but the derivative of the inside is 1, and the derivative of the x plus 1 is just 1. So this is it, and you can see that this is 0. So that then means that your terms go to 0, right? So we're good there. Next, we need to show that it's decreasing. So again, okay, so we need to show that it is decreasing. And so then what we're going to do in this case, you could use the derivative and show that the derivative is negative. But what we could also do is actually use the ratio test, right? Compare a sub n plus 1 to a sub n. A sub n plus 1 is just go and put in n plus 1 in for your n. And I want you to practice that. So that's why I'm going to do it that way, even though the derivative is going to be probably more easier for you. So natural log of, when you replace the n with n plus 1, you have n plus 1 plus 1, so you get n plus 2. In the denominator, you have n plus 1 plus 1, so you'll have n plus 2 there. So that means the ratio of a sub n plus 1 divided by a sub n will be the natural log of n plus 2 times n plus 2 times a sub n, which will be times the reciprocal of a sub n, which will be n plus 1 over the natural log of n plus 1. Okay, which will then be, we'll regroup this and rearrange it and write it as the natural log of n plus 2 over the natural log of n plus 1 times n plus 1 over n plus 2. And by writing it in this form, since the natural log is an increasing function, oh, see, this isn't obvious. I thought this was going to work, but this fraction here, because the natural log is bigger than 1, is actually bigger than, I'm sorry, because the natural log is an increasing function, the numerator is bigger than the denominator, and this one's bigger than 1. But this one over here, the numerator is smaller than the denominator, and that's less than 1. And it isn't clear what it isn't clear what you're going to get when you take a number that's bigger than 1 and you multiply it by a number that's less than 1. And so I thought we could do this using the ratio a sub n plus 1, comparing a sub n plus 1 to a sub n. But once I got here, I realized that I'm stuck, right? Not a big deal, right? We take roads and sometimes they end up in the wrong spot. So let's just go ahead and not do that, right? So, and again, we will we learn from some of the wrong turns that we take as well as from the right turns. So let's go back, and we need to show that it's decreasing, and so then we'll go ahead and use the derivative. So f of x is equal to the natural log of x plus 1 divided by x plus 1. So then again, we want to show that the derivative is negative. And again, it doesn't have to always be negative. It just has to eventually be negative. So f prime of x is equal to quotient rule. So we're going to do the derivative of the top, 1 over x plus 1 times the bottom left alone, x plus 1. And so we're just going to get 1. Minus the derivative of the top is, I'm sorry, the derivative of the bottom is 1 times the natural log of x plus 1 all over the x plus 1 squared. Okay, so the denominator is always positive. We don't have to worry about that. We just have to find the critical numbers. So we have to figure out, what do I put in for x so that 1 minus the natural log of x plus 1 is 0. So I'll do that over here. 1 minus the natural log of x plus 1 equals 0. And again, we will go ahead and add the natural log of x plus 1. Then we will exponentiate to get rid of the log. And so then we will get e is equal to x plus 1. Subtract 1 from both sides. So x is equal to e minus 1. Okay, so then that tells me then that my only critical number, again, is we're only interested in from 1 on. E minus 1 is going to be a little bit more than 1. And so then there's e minus 1. So our inputs start here at 1. So that's why I have this 1 here. And again, eventually, once we get past this number, the natural log is going to be bigger than 1. 1 minus that number is going to be a negative. And actually, right here, if you pick a number between 1 and e minus 1, you'll get a positive if you put it into here. So then, but eventually it's decreasing, right? So this tells you that it's decreasing, therefore your series converges by the alternating series test. So we saw that we tried to use calculus. We tried to use the ratio a sub n plus 1 over a sub n to show that it was decreasing, and it didn't pan out well. But then we used the calculus and everything worked out. And so then you might be wondering why don't we just always use the calculus? Why do we want to use that ratio? Well, in this expression here, and in this next problem here, you have a sub n is 1 over 2n plus 1 factorial. There isn't a corresponding calculus function that we could take the derivative of. So here we have to use the ratio a sub n plus 1 to a sub n. So first we have to figure out what a sub n plus 1 is. Well, we just go and we substitute in an n plus 1 everywhere you see an n. There's a n right there, and it's being multiplied by 2, so now the n plus 1 gets multiplied by 2. And then you have plus 1, and then you have factorial. And so then this works out to 1 over 2n plus 2 plus 1, 2n plus 3 factorial. Okay, and so now we're going to look at the ratio of a sub n plus 1 divided by a sub n. And if we can show that this is less than 1, then my sequence is decreasing. Then we'll show that the terms go to 0, and then the series will converge. So again, a sub n plus 1 divided by a sub n is just to take a sub n, a sub n plus 1, 2n plus 3 factorial, and multiply by the reciprocal of a sub n, which is 2n plus 1 factorial over 1. And again, you have a factorial in the numerator and a factorial in the denominator. The biggest factorial is in the denominator. And so how we clean these up is we start breaking off factors of the factorial until of the bigger one until we get to the smaller one. So 2n plus 3 factorial means 2n plus 3 times the integer before this, and the integer before this one is 2n plus 2 times 2n plus 1. But then that matches with what's on top, so we stop there and just call it the rest of it factorial. And then you have 2n plus 1 factorial, and then the 2n plus 1's factorials go away. So this works out to be 1 divided by 2n plus 3 divided by 2n plus 2. And again, we're only putting in 0, 1, 2, 3. And so at 0, you get 6. at 1, you get 6 here, and you get 2 here. I'm sorry, no, you get at 0, you get 3 here and 2 here, so you get 6. And then at 1, you get 5 here and 4 here, so you get 20. You can see that the denominator is always going to be bigger than 1. And so that means then that 1 divided by that will be less than 1. That should be pretty clear that for any of the numbers that we're using, 0, 1, 2, 3, 4, this fraction will be less than 1, therefore decreasing. Right? And so then the limit as n goes off to infinity of the a sub n, and will be the limit as n goes off to infinity of 1 over 2n plus 1 factorial. And again, you may not have recalled seeing anything like this before, but if you see what's going on once you're putting in 0, 1, 2, 3, 4, 5 and asking what's happening as n gets bigger and bigger. Well, as n gets bigger and bigger, the 2n plus 1 gets bigger and bigger, and then when you factorial it, that gets bigger and bigger. That just makes it get even bigger, and so the top is staying fixed at 1, the bottom is growing without bound. The answer is 0. There's no work to show there. The geometric argument that I showed you as to why the series converges also tells you something else. If you go back and listen to that and go over that, it tells you that what this theorem is saying. If a convergent alternating series satisfies the condition that an plus 1 is less than or equal to an, then the absolute value of the remainder Rn involved in approximating the sum S by Sn is less than or equal to the first neglected term. That is S minus Sn. The absolute value of S minus Sn is equal to the absolute value of Rn, which is less than or equal to An plus 1. So all this theorem is saying is that since you're bouncing back and forth between the, let's go back to the picture. Right? Since you're bouncing back and forth to the left of the limit, to the right of the limit, to the left of the limit, to the right of the limit, your error between your actual sum and what your Sn is always going to be less than whatever that first term that you neglected is. That's all that's saying, right? And so that's what this theorem is saying. So let's apply this. So approximating the sum of an alternating series. In exercises 31 through 34, approximate the sum of the series by using the first 6 terms. See example 4, right? So this is an infinite series. It goes on forever and ever. But we can approximate this by stopping anywhere along the way. And what we're going to do is just put in the first 6 terms, right? So again, what this does, it causes it to alternate, right? So because of the n plus 1, it's going to start positive. So we're going to go 1, and then 3, and then minus, and then 2, and then 9, and then plus, and so then we will go 3, and then 27, and then minus, and 4, and then 81, and then plus 5 over 243, and then 3 times 243, 729. Okay, and so then we can punch that into the calculator. 1/3 minus 2/9 plus 3 over 27 minus 4 over 81 plus 5 over 243 plus 6 over, I made a mistake. Minus, plus, minus, plus, that should be a minus. It's supposed to alternate. So that should be a minus. Minus 6 over 729. And then math 1. The problem, the calculator tells me that this is exactly 5 over 27. Okay, but this is only an approximation. And what the theorem tells us is that the actual value, we're off by a little bit. That's called the remainder. However much you're off by is called the remainder. And what the theorem tells us is that we're off by less than the next term. And so the next term would be 7 over, and 729 times 3, 2187. 2187. So 7 divided by 2187 is 0.0032, right? That is less, our error is less than 7 over 2181. I'm sorry, 2187. Okay, that's kind of cool. We can get how close we are. We're within 7 over 2187 of our answer when we say that our answer is 5 over 27. In this next problem, it says an exercise is 35 through 40. Use theorem 9.1.5 to determine the number of terms required to approximate the sum of the series with an error of less than 0.001. Okay, so we're trying to figure out the number of terms. So we're trying to figure out n so that a sub n is less than 0.001, right? And so your a sub n is given to you by the formula 1 over n squared. And you want this to be less than 0.001. So as we've done earlier, we can flip both sides of this inequality. So 1 over n squared is going to be less than 1,000th, tenths, hundredths, thousandths, then n squared needs to be more than 1,000. And then if we square root both sides, because the square root is an increasing function, this preserves the inequality. So on the left we will get n, and on the right we get the square root of 1,000 is 31.6. So n needs to be greater than or equal to 32. And as long as we are greater than or equal to 32, then we will be fine. Okay, so you need 32 terms. Once you get past 32 terms, you will be within 1,000th. Okay, so does the series converge or diverge? So let's look at this example. Take a moment to pause the video and ask yourself, is this an alternating series? Why or why not? What do you think it does? Does it converge? Does it diverge? And why do you think that? Okay, so this is not a alternating series. An alternating series is going to alternate plus, minus, plus, minus. For some values of n, this series will be positive. For some values of n, the term will be negative, but it doesn't go positive, negative, positive, negative. There's sometimes positive, sometimes negative. But what you should see is that it does have an n squared on the bottom. And the cosine function bobs up and down between -1 and 1. So this looks like uh, uh, it should converge because 1 over n squared is a p series with p being 2, so it converges. The problem is that we can't use a comparison test because the comparison test was only supposed to be used with positive terms. And this has both positive and negative terms. But here's what we could do. We could look at a sub n is equal to the absolute value of the cosine of n over n squared. And by looking at this, then now we only have positive terms, right? And now we can compare that a sub n, I'm sorry, since the cosine of n is between -1 and 1, then the absolute value of the cosine of n is between 0 and 1. So then that means then that a sub n, that the cosine of that the absolute value of the cosine of n is between 0 and 1. Okay, and if we divide both sides by n squared, or all three sides by n squared, then we end up with a sub n is less than or equal to 1 over n squared. 1 over n squared, the series 1 over n squared converges. It's a p series. Therefore, the series cosine of n over n squared absolute value converges by the basic comparison test, right? So this thing converges since it's less than this convergent series. But then you might be saying, yeah, but what about the one without the absolute value? But if you think about it, in the original series, in this series, you have both positive and negative terms. So it should make sense that this sum here should always be less than or equal to this sum here, and it should be between this sum and the negative of this sum. And so then if this one converges, so does the negative of this one, because you can just factor out that negative. And so then the one in the middle has to converge. The one that has both positives and negatives has to converge, because with both positives and negatives, you have some cancellation going on. But over here, they're all positives. The magnitude of the sum just keeps getting bigger and bigger. So if you absolute value, it should be harder to converge. And so then, therefore, it seems reasonable that the summation from n equals 1 to infinity of just the cosine of n over n squared converges. Right? And so that's what we're going to do sometimes so that we can go back to our test that we have for only positive series, and we're going to absolute value, because if it converges with the absolute values, then it should be clear that the series without the absolute values is also going to converge. And so that's what this theorem is telling you. If the series converges, if the series of the absolute value of the terms converges, then the series also converges. And so we have some definitions. Definitions of absolute and conditional convergence. The series a sub n is absolutely convergent when a sub n converges. The series a sub n is conditionally convergent when a sub n converges, but the absolute value of a sub n diverges. Does the series converge absolutely? Does it converge, right? So basically, what you should get is that it is more difficult for the series of just positive terms to converge, because then you just have um, uh, positive values that may or may not converge. So I'm sorry because you just have positive values, and when you add them, it just makes the sum bigger and bigger. Whereas if you throw in some negatives, that could bring down the sum and possibly make it converge. So you should look at this series. You should recognize that you get from so if we look at just the absolute values, we get 1/3 plus 1/9 plus 1/27 plus 1/81 plus dot dot dot. You should recognize that you get from one term to the next by multiplying by 1/3. And since that's the case, it is a geometric series. And because it's geometric, then it converges. Geometric. Therefore, geometric. R is equal to 1/3. Therefore, converges. Therefore, converges absolutely. And so then, if it converges absolutely, the alternating series is also going to converge, right? Because it's more difficult to converge absolutely. Does the series converge absolutely? So absolutely, you would be looking at 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And this is the harmonic series. This series you should have memorized as a series that diverges. It's a great counterexample for people who think that just because the terms go to 0, the series has to converge. Here the terms go to 0, but the series diverges, right? We've already shown that. You can use the integral test to show it, but we've shown it in a different way. But the series itself, because series 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 converges by the alternating series test, right? So again, it did not converge absolutely. That's more difficult when you look at the original series that did converge by the alternating series test. Show that the series converges. Again, we can't use the test that we had before because the terms are both positive and negative. So what we can do is we can look at a sub n is equal to the absolute value, or I'm sorry, a sub k, to be the absolute value of the sine of k, all divided by k cubed. All the terms are positive. So then the sine of k is bigger than 0 and less than 1. And so then when we divide both sides by k cubed, so we've just shown that the sine of k, absolute value of the sine of k, is less than or equal to 1 over k cubed. The series 1 over k cubed converges. Therefore, the series absolute value of the sine of k over k cubed converges. Therefore, without the absolute values, converges. Okay, that's how you do that. classify each series as absolutely convergent, conditionally convergent, or divergent. Okay, so again, it is more difficult to show that a series converges absolutely. So that's you should try first. If it converges absolutely, then you're done. It's absolutely convergent. If it doesn't converge absolutely, you still have to test to see if it's uh, uh, conditionally convergent, to see if it converges because of the alternating series test, right? So here, um, if we take the absolute value, all that is going to do is get rid of the -1, and you're just going to get 1 over k to the 4/3. P series, p is bigger than 1. Therefore, converges. Okay, and so therefore, right, converges absolutely, and you're done. If it converges absolutely, it's convergent. If it doesn't converge absolutely, it might converge by the alternating series test and be conditionally convergent, or it might be divergent. But once it converges absolutely, then you're done. Okay, so again here, you end up with the series 1 over k factorial. This is not a series that we have memorized, but what we can do is we can compare k factorial to k squared. And so k factorial is bigger than k squared. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. But k squared, 1 squared is 1, 2 squared is 4, 3 squared is 9. And so you can see, well, let's come over here. K factorial, k squared. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120. K squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and you can see that it doesn't work until 4, but once you get past 4, 5 squared is 120, 5 factorial is 120, k squared is is uh, um, 25. For 6, you get 720. And for 6 over here, you get 36. That k squared is never going to catch up, right? Now, so, but you can say, look, it doesn't work for the first 3 terms, or for the actually for the for the first 3 terms. But the first 3 terms don't matter, right? So k factorial is bigger than k squared, for k is bigger than 3. So as long as you and so then the first 3 terms don't matter. So then what you've just shown is that so 1 over k factorial will be less than 1 over k squared. And so then by the basic comparison test, then the series converges. So the summation of 1 over k squared converges because it's a p series. Therefore, the summation of 1 over k factorial converges. Therefore, converges absolutely. Now, if you really wanted to make sure that that k factorial was always bigger than the k squared, you could have divided it by, let's say, 9. And then in that case, uh, that would always be true. And that factor of 1/9 wasn't going to make a difference, right? Now, it wouldn't be obvious to prove, but you could see it from the table that that k factorial is going to grow much faster than the k squared. Okay, so classify each series as absolutely convergent, conditionally convergent, or divergent. Again, here, first thing we do is we look at the series of 1 over the square root, and I'll go ahead and distribute k squared plus k. And again, here, we can ignore this k right here. And if that k wasn't there, if it'd be 1 over the square root of k squared, that would be 1 over k. And that is the harmonic series, which diverges, right? So our gut should tell us this series diverges. I don't want to use the basic comparison test to show that this series diverges. I don't want to use the integral test. We're going to use the limit comparison test because of the complicated nature of this series. And so we're going to compare this with 1 over k. So then again, for the limit comparison test, you're going to take the limit as k goes off to infinity of a sub k divided by b sub k. And this will be the limit as k goes off to infinity of the a sub k is the original one, square root of k squared plus k. Okay, and then the multiplied by the reciprocal of, so let me go ahead and put this here, b sub k is 1 over k. So the reciprocal of b sub k would just give us a k over 1. And then this doesn't have a square root, so we can square it and then square root it. So let me go ahead and undo that. Okay, let's do that in red. We can square it and then square root it, and so we haven't changed the problem. And so then this becomes the limit as k goes off to infinity of, since both the numerator and denominator have a square root, we can put the square root over here and get k squared over k squared plus k, rational function. So then this is the square root of 1, which is 1. Therefore, since the 1 over k diverges, the series of 1 over the square root of k squared plus k diverges. So it's not absolutely convergent, that's what that just showed, but it could still be conditionally convergent if the original series converges. But I'm not going to go through it because it should be fairly clear. It's alternating, it's decreasing, the denominator just keeps getting bigger and bigger. The terms are going to 0, and so then this converges. By the alternating series test. Therefore, we're supposed to classify it. It's conditionally convergent. Let's move on. Okay. Here we have this cosine of k pi. Notice that it is k pi. The cosine of 1 pi is -1. The cosine of 2 pi is +1. The cosine of 3 pi is -1. And so this was just a clever way of putting in that factor of -1. It started out negative and k starts at 1, so we go to the k and then k over k squared plus k. So when we look at the absolute value to see if it converges absolutely, all that does is get rid of this factor of -1 to the k, and so then we're just looking at the series k over k squared plus k. Okay, and so again, what I told you is that you can pretty much ignore all but the fastest growing terms in the numerator and denominator. So we can ignore this plus k here. And if you ignore that, you just end up with k over k squared, which is 1 over k again. And then that means then that you're going to compare this to um, the series 1 over k, which diverges because it's the harmonic series. But adding k to the denominator makes the term smaller, and so the basic comparison test is going to be a little challenging. So again, we'll use the limit comparison test. If it was a minus k, then it would be easier to just use the basic comparison test. But because it's got that plus k, we're just going to go ahead and use the limit comparison test. And so again, we're going to take the limit as k goes off to infinity of the a sub k divided by the b sub k. Which one is which does not matter. This becomes the limit as k goes off to infinity. I will use this one here as my a sub k. So k over k squared plus k times the reciprocal, which would be k over 1, which then becomes the limit as k goes off to infinity of k squared over k squared plus k, which is then equal to 1, same degree in the numerator and denominator, so your limit is 1. Therefore, both diverge. Right? But again, so that means it's not absolutely convergent. When you look at the absolute values, the series you get does not converge, so it's not absolutely convergent. But here again, the terms are going to go to 0 because the degrees of the top is smaller than the degree of the bottom. You have a k squared plus k over k. I've already gone through showing how using the ratio test, or you can use the derivative to show that that's decreasing. But it should be, fairly intuitive that this is decreasing since the degree of the denominator is bigger than the degree of the numerator. So this is decreasing, and the terms go to 0. So because it's alternating, this converges by alternating series test, therefore conditionally convergent. Okay. Now you should have some intuition as to how fast things grow. You should see that in the numerator you have a exponential function um, with a base of 3. And so that's going to grow pretty quickly. So as k goes off to infinity, that numerator is going to go off to infinity. So no need to start looking at the absolute value right away. When you see this problem, you should see the base is 3. This exponent is going to get bigger and bigger, so that goes off to infinity. And on the bottom, you just have a quadratic. And so you should know that you should have built up some intuition that this fraction here is not going to go to 0 because the numerator is growing much faster than the denominator. We could show that with L'Hopital. So we can look at the limit as k goes off to infinity of 3 to the 2k minus 1 over k squared. Again, we're going to use L'Hopital, so we have to change this to the limit as x goes off to infinity of 3 to the 2x minus 1 over x squared. And again, we have an exponential function, so the derivative will be the limit as x goes off to infinity of the derivative of anything that's not e to the x has an extra factor of the natural log of the base times same 3 to the 2x minus 1 times the derivative of the inside 2. And on the bottom, you get 2x. But you still have infinity over infinity. This is still going off to infinity, so you have to apply L'Hopital's again, and this becomes the limit as k goes off to infinity of, now you're going to have another factor of the natural log of 3 squared, and you're going to have another factor of 2, 4 times the natural log, I'm sorry, times no natural log, times 3 to the 2x minus 1. And in the denominator, you're going to have 2. Right? Actually, I could have just canceled those 2's out, but I didn't. But either way, now the numerator is going off to infinity, so this is infinity, therefore diverges. Right? This thing diverges. The original series diverged, so definitely the absolute values is not going to diverge. The terms have to go to 0. Here, the terms do not go to 0. So we're done. There's your homework for this section. Please stay on top of the class. When we resume, we will pick up where I leave off on these videos. You know, I know this is difficult, but try and do a little bit at a time. Get up, stretch, take a break, try some homework, come back, and most importantly, be safe.